So, welcome to third week to today's session of state-based approach to control system analysis. I am Srishi Siddharth. I am IT for this course. So, uh, 3.3 process before we look at examples. So, the first one would be computation of state transition wickets. Computers using the exponential series or the matrix exponential series. Also calculated using the Laplace transform. Or using the process of factorization. That solution of LTI and LTV systems. We'll discuss discretization, which consists of zero order whole approximation. And discretization using the Euler scheme. Okay, so let's begin with the state transition models. So if we have a homogeneous system, x dot equals ax. So homogeneous means that there is no input, which will be 0. So for LTI system, this is a constant matrix. And let's say if there was only one state, then A would be a real number. Then the solution to x dot equals ax would be simply xt equals a to the power p x times a. Now, if there are some n states, then A would be a square matrix of size n by n. And then the solution of x dot equals ax would be e to the power at x0. And in this case, this is the matrix exponential. So the solution to the system x dot equals ax is xt, x at time t, is e to the power at times x0. There are n states, and this is known as the phi t, which is a state transition matrix. So if you are in the state space, let's say this is Rn, this is some initial condition. Then on applying phi t, you get to the state x of t. In a more general notation, if t equals t naught is the initial time, then xt is e to the power a, t minus t naught, x t naught, and this is phi t comma t. Alright. So if we have an LTI system, then phi t is simply Laplace, which is e to the power at, is Laplace inverse of Si minus A inverse. We have already looked at how to compute inverse of a matrix in week 1, and in week 2 we saw how to compute Laplace inverse while we were talking about diagonalization. So this is okay. Let's move on to a simple second order question and second order system. A is 0, 1, minus 2, minus 3. While input for a free response, we will not need the vector B. So we have A. So to get the state transition matrix, so for computing the free response, we need the state transition matrix and some initial conditions. So let's compute 5. For this, we have Si minus A, which is S, x plus 3. And then we compute the inverse of a 2 by 2 square matrix, right? So it's 1 upon x squared plus 3s plus 2. So this is s plus 1, s plus 2. Alright, so to compute the Laplace inverse, observe that we need Laplace inverse of, let's see, s upon s plus 1, s plus 2, and just 1 upon s plus 1, s plus 2. So using the Laplace inverse of these two quantities, we can find out Laplace inverse of every element of the matrix Si minus A inverse. Alright, so let's begin with the simpler one. So 1 over s plus 1, s plus 2. Minus 1 over s plus 2 computed at minus 1. Similarly, C2 is 1 upon s plus 1 computed at minus 2. This one. minus 1 over minus. This is simply e to the power minus t minus e to the power minus 2t. This is 2. Now it's perform partial fraction expansion of this quantity. Alright, so C1 is so this becomes just make sure to check the sign of the equation. So let's say minus t plus 2 e to the power minus 2t. So using these expressions, we can calculate the Laplace inverse of Si minus A. This is so let's simplify this. This is 4 e to the power minus t. Right, now to compute the free response, so we can assume any initial condition and then post multiply by this matrix. So this is this is some x1 0 and x2 0. So given some initial condition, we can find the solution at any time t. Now let's look at a higher order system. What is 0 0 minus 2? The initial condition at 0 equals 0 1 0. So compute the free response of the system. So compute 5t. So t comma 0 and so we have Si minus A. This is S minus 1, S minus 3, and then 0, 2. We discussed in the last tutorial how to compute the inverse of matrix. So I'm going to do the calculations and verify that the expression for Si minus A inverse, which is the adjoint of Si minus A over determinant of Si minus A. Or if you have any other method to compute the inverse of a large matrix. So I'll write down the state transition matrix directly. Phi t. So observe that we have positive parts of t. So if we have the initial condition and solution is, so for initial condition 0, 1, 0, this is equivalent to selecting second column of e to the power t. So this is 0 e to the power t 0. So you can see that as time increases or time goes to infinity, xt also goes to infinity, or the solution blows up. So the entries of the state transition matrix also help us to determine whether the solutions of the system would converge to the equilibrium or zero or blow up as time increases. So this is fine. Let's move on to another question. It's for homogeneous system. Now let's state transition matrix and the solution of homogeneous system. Then we have non-homogeneous system. In this case, we consider the solution when there is an input here. So when x is equal to x plus b, and the initial conditions at time t0, the solution is given by okay. So in terms of the state transition matrix, you can write this as phi t comma t naught or t minus t naught. So t minus t naught x naught plus t naught to t phi t minus tau b tau beta. Okay. So this is in the time domain form, or if you have, we can also use Laplace inverse to get the solution. So xt is Laplace inverse of Si minus inverse times I0 plus Laplace inverse of phi s b inverse. So this solution, part of the solution is due to initial conditions. This is the solution due to input. Okay, so let's look at a question. So let's assume that U is a step input. So UT is defined as 1 for all time greater than equal to 0 and 0 other times. This is 1. This is a step input. Okay. So look at this matrix. We have already calculated the state transition matrix for this. So e to the power 80, which is Laplace inverse of is given us. So now we need to calculate the Laplace inverse due to input. Right? So let's see. Or Laplace inverse or the integral. So we have time 0 to t. T naught is 0 in this case. We have t minus tau b Newton. Okay. So for any time greater than 0, this is always 1 and b is given to be 0, 1. Okay. So when you multiply by e to the power t minus tau, which is substituting t minus tau here, and then post multiplying by this vector, you will get 0 to, sorry. So we are selecting the second column of e to the power at minus tau. Okay, so this is easier to integrate because these are integration of exponential functions. So I write down the solution directly. This is half e to the power minus t. So to verify, let's check the integral of the integration test. So this is 0 to t. F e to the power minus t times e to the power tau deta. This and similarly, you can compute the integration of other terms. There are four terms. This, so these are the same. This and this. Alright, so We still have to find the solution. So let's assume some initial condition. Let's say that at 0 and the system was at the origin. So T in between 0 plus this whole this is okay. So after multiplying by the vector 0 0, this is identically 0, right? So the only solution is due to the input, which is so the only solution is the forced response. On to another topic, which are the properties of the state transition matrix. We recall that at time t equals 0, xt is exactly xt, right? So in general, xt is phi t times x0. So this must be identity of size n by n. So this is the first property, that at phi 0, it's identity. I'll list down the properties of the state transition matrix. This is phi 0 is identity. Now xt is phi of t times x0. And since this is the solution to the state space model, the derivative to satisfy the differential equation, right? So this is a times x of t. This can be written as a phi of t x0. So comparing the matrices which are multiplied by the initial state, we get phi dot t is a phi of t. This is dy dt of phi. Alright. The next property is that, let's say that this is s dot equals ax, and at time t equals 0, this is x0. Of t1, let's say x of t2. So using the solution, x of t equals e to the power at x0, we have x at t1 equals e to the power t1 x0, and x of t2 is write this down in terms of state transition matrix. So we know that this is directly phi of t1 comma x0. So this property says that if we have the state at T1, then we can go to T2 using the solution at T1 and the state transition matrix at T1. So this would be T given the value of T1 times x of T1. And we won't have to use the initial conditions. So uh, the trajectory in two parts, 1 and 2, is equivalent to xt equals e to the power at to x. So let's see. That T2 is phi of T2 minus 0 times x0. Ft2 is also phi of T2 minus T1 at xt. So this is phi T2 minus T1 x of T1, which is phi T1 minus 0 x0. So this is T2. So comparing this and this, since we are talking about the solution at T2, so phi of T2 is phi T2 minus T1 and phi T. And if time T naught is not 0, then this would be T square. And then we also have, let me write this as phi of T2 minus 0. This is T naught. So this is the composition. So first we get the T1 and then multiply by the state transition matrix to go from T1 to T2. And the next property is phi of minus T. That is to go backwards in time. This is simply the inverse of the state transition matrix at T. Let's look at a question here, which uses the properties of the state transition matrix. So this is question 4. So let's say that there was a system. So that system was defined by the matrix A. We don't know what the matrix A was, but we know what's e to the power A. So this is given as 1 plus 2b e to the power 80 and A is a scalar or a real number. So let's check if uh, get anything from substituting t equals 0. So phi of 0 should be identity, right? So this is, let's check if this is a state transition matrix. So this becomes 1. So substitute t equals 0 in this matrix. This is 0. Okay, so this is not 4 plus, but it is 4t times to the power t. This is 0. And then this is 1. Okay. So now we need another property of the state transition matrix, which is d by dt of phi t, which is a times phi t, and compute this at equals 0. So let's see what's So we are doing this because we know that A at time 0 is just A because we're talking about an entire system and phi 0 is identity. So this is equal to A. Let's compute the derivative of this matrix. This and then compute it at t equals A. This is e to the power this minus e to the power t with A times then just 4 times e to the power t plus 480 e to the power t. Then this is minus 2 e to the power 80 plus 1 minus 2t times A e to the power 80. This is 2 plus A, and then we have minus 1, and this is 4, and then we have minus 2 plus A. So this is the matrix. So similarly, let's look at another question. It's just okay. So e to the power 80 is so let's see phi t, which is this. So phi 0 is identity on that, right? So this is 1, and this is 0, 0 and 1. Yeah. And we've just seen that d of phi t computed at t equals 0 is limited. So let's complete the derivative which implies this is time t equals 0. We have so we have minus 6 plus 2 and minus 6 plus 5 and then minus 1. So this is the matrix A. So to verify by calculating pi of t using this A. We should get the same answer as given in the question. And one the question on solution of LTI systems. So question 6. Solution of LTI systems. Just a second. Alright. Okay, so consider the following. Time varying system, linear time varying homogeneous system. So we're not considering any input antenna. This one dot initial conditions are from Z1 and Z2. So observe that this is the time varying system matrix AFT, and these A's are just scalars, right? Because this is a 2 by 2 matrix. Let me just write this one more clearly. This is correct. Determinants where A is a 2 by 2 matrix. This is actually process 4 by 4. Each state x1 has two states inside it. So A is a 2 by 2 matrix and Z1 and Z2 are vectors of dimension. The column vectors size to the each of Z1 and Z2 is a column vector of size to the The first part is compute the solution, which is x1t and x2t. Second one is to compute the system's state transition matrix. Five two comma table. Okay, so observe that the time varying matrix A is lower triangular, right? Alright, so let's see if we can use this to compute x1 and x2 by decoupling the two states. So let's say x1. So x1 dot is simply A times x1 and x2 dot is A times x1 plus A times x2. So if we know the solution of x1 from this equation, we can substitute in the second equation to get x2, right? Observe that since A is a constant 2 by 2 matrix, let's say this is the first and the second. First is an LTI system. So this means x1 at time t simply e to the power a t minus t naught x1 at time 0 or t naught, right? So let's remove t naught. This e to the power at times z1. Okay. And now for the second system, this acts as an input and this is the system matrix which is constant. So this means that x2t is simply e to the power a t times z2 plus x0 to g e to the power t times b. B in this case is so b u tau is given as tau a into x1. So let me check if it is there. Yeah. So substitute the expression for x1 at tau. This is tau then e to the power a tau and a minus tau cancel and we have e to the power a t times f2 plus integral tau a z1 beta. At a z1 times t square by 2. So this is the solution x2 at any time t. So observe that the solution of x1 only depends on the initial condition of the first state, but the solution of the second state depends on z1 and z2. And the second part was to find out the state transition methods, right? So you can compute, since it's an LTV system, you can use the exponential series and plug terms of each of the elements of the matrix, or essentially we have the state transition matrix as the relation between the state at t and this vector, right? And observe that we already have the solution in terms of Z1 and Z2. So let's write down this state transition matrix. So this is e to the power at 0. Then it's t squared by 2 e to the power at times a times Z1 Z2. So this is the state transition matrix. Okay. So just check if you have completed this correctly. You can verify using the property that phi of 0 should be identity, right? So let's check. This is identity 0, 0 and identity. So substitute t equals 0 in this matrix. Alright. This question is about state transition matrix to get the system matrix from a state transition matrix for an LTV system. So this is question 7. Such that the state transition matrix phi t with initial time t naught is 1 exponential t square minus t naught square by 2 minus 1 0 and then so such that this is the state transition matrix. The homogeneous ribbon. X dot equals a as a function of time times x. So all of these are functions of time. So this is x dot t. Alright. So let's check if we have the correct state transition matrix. Phi at t naught comma t naught would be 1. Just substitute t naught in place of t. E to the power, let me check. Okay, I think there is a typo here somewhere. 0 and sorry. This would be after substituting e to the power 0 minus 1. Right. And this is 1. Okay, so this is correct. Now we have the property that the matrix AT times phi t is d by dt of phi. Right. So this is true, and it's true for all time. So we compute this at time t equals 0, so that we can make use of the identity that phi of 0 is identity. So for an LTV system, what we get is a at time 0 is d by dt by t. So compare this with an LTI system. Since a is always a constant, a at any time t is d by dt at equals 0 by t. Okay, so let's differentiate the matrix. This is and this is at t naught. So d by dt of phi t is 0 is t naught. This is 0 and again the same quantity. This becomes 0 minus t naught e to the power. I hope I might just let me check this. Sorry. This is no. To differentiate with respect to t. So this is 0 exponential t square minus t naught square by 2 times t and 0 and in the same quantity. At t naught, this will become t naught 0 and t naught exponential to the power 0. So this is a at time t. So I hope that the state transition matrix is clear to you. Now let's move on to another question. Just a second. Topic is that we have already seen how to compute the state transition matrix using the Laplace inverse approach. And for example, for an LTV system, we actually were able to solve the differential equation and get the state transition matrix. Now let's look at another method. So this is fourth. State transition matrix using diagonalization. And so recall that e to the power at for matrix A, which is of size n by n, is given by can be written as e to the power at p e to the power, let's say, lambda d p inverse. So p is the nodal matrix, which is obtained using the eigenvectors. Yes. and e to the power lambda t is constructed using the eigenvalues of the matrix A. So let's say there were n eigenvalues for an nth order system, and all of them are distinct. So this is lambda 1, lambda 2, till lambda n, and 0 is everywhere else. So this is the main diagram. So let's look at an example which we've already seen before. We have computed the state transition matrix using the Laplace inverse. And now let's see if we can get the same matrix using diagonalization. So this is question 8. So consider the system. X or equals 0, 1, minus 2, minus 3, x, and initial state is 0. Okay, so we already know calculate the state transition matrix. So we know that 5t e to the 5t is Laplace inverse of. But then we also saw that for a larger system, for example, if the matrix was 3 by 3, then we have to calculate the inverse of this matrix, right? And also for any higher order system with even 3. The other approach is to diagonalize the system. So to diagonalize, we first need the eigenvalues of the system, and those are the roots of the characteristic equation. This is determinant of matrix minus lambda minus 3 minus lambda 1 minus 2 equal to 0. So this becomes lambda square plus 3 lambda plus 2 equals 0. So lambda is this is minus 1 and minus 2. Okay. So what would be e to the power 80? Would be then that so exponential of a diagonal matrix, which is simply sorry. So this is incorrect. This is simply the matrix lambda. And if it's a diagonal matrix, you can actually see by expanding e to the power lambda t as that we'll have non-zero values only at the main diagonal, right? And this is e to the power lambda 1t e to the power lambda nt. So this is a matrix. But these exponentials are now exponentials of real numbers, e to the power lambda 1t to lambda nt. Okay, so this is e to the power minus t e to the power minus 2t 0, 0, p inverse. So now we need to find out the matrix P. So P comes from the eigenvectors of the eigenvalues. So the first would be the eigenvector for lambda equals minus 1. Because we have actually considered lambda equals minus 1 as the first eigenvalue and then minus 2 as the second one. This eigenvector for lambda equals minus 2. So let's compute these. minus I, which is 1, 1, minus 2, random vector equals 0. So this has only one equation which has v1 plus v2 equals 0. So choosing v1 to be 1, we have 1 minus 1. Similarly, for lambda equals minus 2, a minus 2i and c equals 0. This is 2, 1, minus 2 minus 1. Is 2v1 plus v2 equals 0. So if we choose v2 to be, then v1 would be minus 1. So let's see, this is minus 1, this is plus 1. There are infinite choices for v1 and v2. We can select any number. This is 1 minus 2. So matrix P is 1 minus 1, 1 minus 2. So choose this column so that we can take the inverse of this matrix. So let's check if this matrix is invertible. This is minus 2, that's 1. So P is invertible and P inverse is 1 upon minus 1. So this is simply 2, 1, minus 1, minus 1. Now let's compute e to the power 8. So this is P, then the exponential of the eigenvalues, and then P inverse. Okay, so let's see this becomes e to the power minus t, e to the power minus 2t, so let's see if this is. So this is the state transition matrix. And then you can verify this by calculating or computing either Laplace inverse of S minus A inverse or by computing the matrix exponential of A times T. This is this was for a secondary system. Third equals now we look at when we are repeating eigenvalues or let's say distinct ones. So this 0, 1, 0. And the solution xt. So This is a non-homogeneous case. So there would be a part due to the initial condition and the other part due to the input. So for both of these parts, we need the state transition matrix, and we'll calculate this using diagonalization. So observe that this is in the controllable canonical form, right? This is a chain of integrators, and then we have a non-zero Riemann at the end. So if we have the A matrix in CCF form, we can get the modal matrix P as 1, 1, 1, lambda 1, lambda 2, lambda 3. This is a 3 by 3 matrix. Then we have lambda 1 square, lambda 2 square, lambda 3 square. So if we know the three distinct eigenvalues, we know how to find the matrix P. So this is known as the Van der Waals matrix. So if the matrix is in CCF form, we can get the matrix P. So let's find out the eigenvalues. This would be determinant of A minus lambda. This becomes minus lambda. If we substitute minus 1, minus 1 plus 6. Okay, this is not 0. So if we put lambda equals 1, and 1 plus 6 plus 1 minus 6. So this is also not 0. So let's check if we have calculated the characteristic equation correctly. Okay, so this is plus lambda equals minus 1 in this situation. Now we can get the other periods, right? So this is lambda plus 1 plus 5 lambda. Plus 6. When we have 0. Okay, so let's find out the root of this equation. This is lambda equal minus B. Okay, so the eigenvalues are lambda equals -1, -2, -3. So the matrix P is 1, 1, 1, lambda 1, lambda 2, lambda 3, and then the square of these values. So you can now compute P inverse of this matrix, and the state transition matrix would be P into the power P inverse. So this would be the state transition matrix. Okay, so if this is clear to you, let's move on to another question. And this is question 10. This is like A, B, 0, -2, 1, 3. So we will compute the state transition matrix using diagonalization. So this is, let's compute the eigenvalues first. Square -3 lambda plus 2 equals 8. Alright, so this is 3 plus -1 over 4. So these are the eigenvalues. And e to the power e would be P, e to the power t, e to the power 2t, and P inverse. So P is using the eigenvector. So for lambda equals 1, we have A minus I times P equals 0. Plus 1 minus 2, 1, 2. Is V1 plus V2 equals 0. So we choose V1 to be 2, then V2 is minus 1. So the eigenvector is 2 minus 1. For lambda equals 2, we have A minus 2I times V equals 0. Is 2. 2, 1 and 1 times V1 V2 equals 0. So this is V1 plus V2 equals 0. from both the equations. And if we choose V1 to be 1, we have V2 to be minus 1. So the eigenvector is 1 minus 1. Now the matrix P is P inverse and then compute e to the power 80. So in some cases, if this turns out to be not diagonal, then you can use the expression P inverse e to the power lambda d P. So you have to figure out which one of these two give the diagonal form. So if this is clear, let's move on to discretization. So if you have any doubts regarding the assignment or the questions that we are today, then you can ask me in this session. So let's say that it's much talk about this. Let's consider a system. So only one of the second order systems that we have considered. Take the first one. So the matrix A is 0, 1, minus 2, minus 3. We know the analytical solution of this. We have already calculated it. But now let's calculate the solution using Euler's law. For Euler's method, the general expression is if we have x dot equal f of x times u. So if we have the u input also, then x at the next time instant is x at k plus delta t times start from 0. So we know that 0 is given. At the next time instant, we have x0 plus delta t. And if we have an LTI system, this is simply A matrix times initial condition plus B times the input at 0. And for an LTI system, this would be A x at k plus B u at k. The function f could be any function. It does not have to be linear. It would be like x dot equals, let's say, x square. And this is not an LTI system or an LTV system. So we will not be able to complete the state transition matrix. So in that case, we can find out the solution using discretization. So one of them is the Euler's method. We have to choose two quantities. First one is the initial condition, so that we know how to compute this recursive equation exactly plus one. And we also need the time step definitely. So usually this is small. I think in the lectures this has been taken around 0.01 or a multiple of it. We could also try 0.001 and some lower values as well. Okay, so this is x1 at t plus 1 and x2 at t plus. So this is simply minus x2k. K plus delta t times minus x2k, and we have x2k plus delta t times minus 2x1k minus 3 x2k. X0 and sometimes the delta. Verify this discrete solution. The analytical solution. It has been obtained using the state transition matrix e to the power at, right? Which is xt is simply e to the power at times x0. Now another way of getting discrete solutions using the zero order mode approximation. So let's say if we have a system with the input, I think we have done one question on it. So let's see. Yes. So equals x1 dot x2 dot 0, 1, minus 2, minus 3. So here you take the step in. So let's see how we can compute the solution using zero order approximation. So this is only for LTI systems. However, the Euler's method was for any nonlinear system x dot equals f of x times u or x comma u. So have x at let's say k plus 1 is phi of delta t, where phi of delta t. So you can refer to the lectures. This is e to the power a delta t. Gamma k is integral of 0 to delta t e to the power a mu b k. The assumption is that in the time interval k to k plus 1, the input ut remains constant. And is u at k. So it can be taken outside this integral. So we know the state transition matrix at any time. We can substitute delta t and get e to the power a delta t. So let's do that. Phi delta t. Just a second. Sorry. E to the power minus delta t minus e to the power minus 2 delta t. So I'm just substituting delta t in place of t, and this becomes so we can choose delta t to be any value and substitute to get a numerical value of phi of delta t. So in case there is sorry, this is actually a bit different. So in case of uniform sampling, I think so. We will compute this for uniform sampling. At k plus 1 is simply phi of capital T xk plus gamma t uk. So phi t is e to the power at and gamma t is 0 to t e to the power in each. So in case of uniform sampling, just substitute capital T and we get substitute the value of capital T and get phi of capital T, and gamma of T is pi a mu. So I have to substitute mu in terms of T now times B. So B is 0, 1. So we are selecting the second column of e to the power a mu. So let's write that down directly. This is e to the power minus mu These are exponentials. We can compute the integrals easily. This is minus this is e to the power minus 2. We can calculate this at 0 and t and substitute the values to get gamma t. And therefore get this Discrete equation at k plus 1. This is, let's substitute this becomes this is gamma t. So substituting this and 5t, this is 1, 2 and 3. So substitute 2 and 3 in 1 to get the discrete equation at uniform sampling rate t. Sorry, 1 over t. Alright, so these are all the questions for today. If you have any doubts, then please let me know. Then you are free to leave. There are no more questions. That's all for today. Thank you.